This moving walkway problem is an example of a distance, rate, time problem in which it is helpful to create a table. And generally we label these columns D, R, and T for distance, rate, and time. And over here on the left we write down the two moving bodies, or in some cases the two directions. This describes Enrique walking from his gate to the newsstand and then returning to his gate. So this is in one direction going with the moving walkway or on the walkway, and in the other direction just on foot. Of course, on the walkway he is also on foot, but on foot in this case means only on foot. All right, so here we've got some information to use. The distance is 200 feet, and it looks like he goes to the newsstand the full 200 feet, and then back, which is another 200 feet. Because it's the same trip, both distances in this problem are the same. The moving walkway travels at a rate of 5 feet per second. So it's important to note here that my distance is in feet, as I indicated, 200 feet. My rate is in feet per second, which means my time needs to be in seconds. And because the time needs to be in seconds, we gave a little hint in the problem saying that if this round trip time is 1 minute, we really should think of that as being 60 seconds. So right now focusing on the rate, to contrast this with those with the wind against the wind or with the current against the current problems, we are not going to add the speed of the walkway in one direction and subtract it in the other direction, simply because we would never walk the wrong direction on a moving walkway. If you were to do that, it certainly could be modeled like a wind and current problem. However, you would most likely get thrown out of the airport because you would be in the way of all the people going the correct direction on the moving walkway. So we're going to set this up with something a little more realistic. That means if we consider the general walking speed on foot to be x feet per second, then with the moving walkway we go x plus 5. So on some of these word problems, it makes sense to add the external force in one direction and subtract it in the other direction, but make sure that that external force really is in play in both directions before you do that. That's generally just on wind and current problem where we're talking about being with the wind versus against the wind, or with the current versus against the current. Now we are going to fill in the remaining column here, which is time, using distance equals rate times time. But again, we're solving this for t. Since time is the last column to be filled in here, I can see that to solve this relationship for t, I would have to divide distance by rate, and therefore I am going to make a ratio out of these two quantities. 200 divided by x plus 5 is the time in seconds on the moving walkway, and 200 divided by x is the time in seconds off the moving walkway, just walking on the floor. So now I'm ready to start thinking about how I'm going to set up my equation, and this is where I look for a description in the problem of the time, since the time is the column that has all of the information. This says the round trip time is 1 minute. This is not a model in which the times should be set equal to each other. Instead, we know how long it should take if I add up the two legs of the trip. So a round trip is the trip out, which is 200 over x plus 5, plus the trip back, which is 200 over x. And this should equal the round trip time in seconds, since seconds are the units of my time, which is 60. So I now have an equation that I can solve, and I'm going to start by finding the LCD, which is x times x plus 5. This is not a proportion, since we have two rational terms on one side of the equation. I do have to multiply the LCD by both sides of this equation. Looking first at the left-hand side of the equation, I can see that the x plus 5 factors would cancel from my first product, leaving me 200 from the numerator and x from the LCD. Looking at my next product, I can see the x factors would cancel, leaving me 200 from the numerator and x plus 5 from my LCD. Looking over at the right-hand side, I can see that there are no denominators, so nothing cancels. So I'm going to take the whole 60x and distribute it into the parentheses x plus 5, and just do this all at once to get 60x squared plus 300x. Now I still need to distribute in on the left-hand side this 200, so we now have 200x plus 200x plus 1000 equals 60x squared plus 300, this 300x. This equation is starting to look just a little bit messy, but it will clean up pretty nicely by the time we combine like terms, get them all on one side, and then look for a GCF. So this term is 400x. Let's just go ahead and combine those and then subtract this from both sides without rewriting the whole equation again. So we will subtract 400x from both sides. And we will also subtract 1000 from both sides to bring this over to the right-hand side, so that now our equation is 0 equals 60x squared minus 100x minus 1000, and I'm going to look for a common factor to take out of the whole equation before looking for the full factorization. It looks like 20 is the greatest common factor of this polynomial, and the resulting polynomial can be factored. This is 20 times 3x plus 10 times x minus 5. Just as a quick check, my first term would be 3x times x, which is 3x squared. My outer term would be 3x times minus 5, which is negative 15x. My inner term would be plus 10x, which when I combine those two would give me negative 5x. And my last term, positive 10 times negative 5, gives me negative 50. You may find that you need a few more steps in order to factor this trinomial, but whatever factoring method that you are using should be fine as long as you can factor it. And the numeric factor of 20 will not be relevant for the equation. A numeric GCF does not contribute anything to the solutions of a quadratic equation. So I'm just going to take each of the factors that have variables in them and set them equal to 0, getting x equals negative 10/3 for the first one and x equals positive 5 for the second one. Since the meaning of x is the walking speed, it doesn't really make sense to have a negative walking speed, so we will go ahead and throw this one out and just keep the value 5. Returning to the original problem, just to see if x is what we want or if something else is, I need to look both at the question, how fast does Enrique walk, and at my variable definition, on foot is x, so it makes sense that the value x that we just found really is our final answer for this problem. I just need to express it with units, remembering that the units here are feet per second. So 5 feet per second is Enrique's walking speed.